Hi guys, so welcome to the first proper lecture of what we're looking into the discretization aspect of the finite element method such that we can solve truss structures like this in a generalized format. So we're going to be doing a lot of this work on pen and paper, very little coding until we actually start to apply this, and hopefully that's going to alleviate some of the confusion that was maybe there from last module. Now, I want you guys to read the introduction of the accompanying notes, which obviously you should do anyway, that accompanies this module, because it explains in greater detail some of the more general aspects of the finite element method. We are just looking really at the discretization aspect of the finite element method such that we can solve this problem. Still super important to be able to determine, and let's just think about what we're trying to do. So even for a simple structure like this, it would be good to be able to solve this in a generalized format. So we want to be able to take any sort of truss structure and define it in terms of two tables. So the first table will be information about where the nodes actually exist. Let's describe this. Let's say I've got a node ID, and I could describe each of these as an x and y coordinates. So let's say y is my vertical, x is my horizontal, and let's say node A is the origin of this axis system, node B exists at 1, 0, node C is at 2, 0, node E would be at 1.5, and it's actually going to be, let's pretend these aren't equilateral triangles, let's make it 1.5 and 1, and node D will be at 2.5 and 1. No, wait, sorry, I got these completely wrong. They should be 0.5 and 1 here. This first one's going to be 1.5, and then this one will be at, this first one is going to be 0.5, and then this one will be at 1.5 and 1. So this information here just describes the x and y locations of each of these nodes. Okay, so this table can be constructed that then helps us describe just where each of these nodes exist, and in order to finish off describing this whole shape, we need to describe where these members actually connect from and to. So we've got 1, 2, 3, 4, 5, 6, 7 members. So we can define another table that defines the actual shape of our structure and defines each member, where it starts and where it ends. So let's say I've got members, and I'm going to put 1 and 2. Okay, 1 is where it starts, 2 is where it stops. So member AB goes from node A to B. Member AE goes from node A to E. And we continue this down. Okay, so this table here describes the connectivity of our structure. So we can then take any truss frame structure and describe it in terms of these two tables, one that describes where the nodes go and one that describes which member connects which part to which other member, which node to which node. And what we want to be able to do is we want to be able to take these tables and construct a generalized problem of the form K, Q is equal to P. Okay, and let's talk about the different parts of this problem. This is a matrix problem, which is just another way of saying we've got a set of coupled equations. So we have a global stiffness matrix. And I think in the introduction lecture I said it would have been n by n, where we've got n nodes. It would actually be, for this sort of problem, it would be 2n by 2n, okay? Because each individual stiffness matrix, and this will start to make more sense, is a 2 by 2, okay? We've then got a vector of generalized displacements, or vector of displacements. And so then Q would look something like AX, AY, BX, BY, all the way to EX and EY. Okay, so we've got a vector that, again, if we've got n nodes, then this would be a 2n by 1 matrix, sorry, 2n by 1 vector. Okay, and then the vector of the so noisy. The force vector, so this is the non-conservative forces on the right hand side of the problem. This would be, for this one, we'd have F, let's call it FXA, or FAX, doesn't really matter how we describe these, FAY, FBX, all the way down to FEY. Okay, so these two are going to be the same shape. So what we're trying to do is we're trying to construct this problem. Okay, and we can't go straight in and do that for a truss structure because we don't know how to do this problem yet. So we're going to look at how we solve this in general, and we're going to look at doing a simple isolated spring. We're going to join springs together, and then we're going to start to make it more complicated. So let's start with the simple spring. Just before we move off, I'm going to make a quick point of distinction here. When the way that I've written these here, you'll see that my K, my Q, and my P are all uppercase letters. Okay, and when they're in uppercase, this means they are in global coordinates. And what do I mean by global coordinates? Well, hopefully you've heard of similar terms like this before, but we can talk about global versus local coordinates in this problem. When we're talking about global coordinates, or the global reference system, this just means we can describe the entire problem. So going back up here, a set of coordinates that describes everything in this problem. Okay. And this means it's relating to the entire structure. And by contrast, what we're going to be developing we're going to be looking at individual members and how the constitutive relationships work for individual members. Those are in local coordinates, or local reference, or in the local reference frame. And this will make more sense when we actually get to construct the problem, but local coordinates, these will be lowercase. Okay, so this will be, for example, I'll have a lowercase k, a lowercase q, and a lowercase p. Okay, so these, if you see terms in lowercase, this means relating to an individual element. And by individual element, we're just talking about an individual member in this case. So hopefully what you can see, and you can maybe start to think about how we're going to be formulating, is if we can define a set or a generalized means to define local relationships for members in a structure, and we can figure out a way to convert those into some sort of global coordinate system, then we can take those equations and put them into a system of coupled equations. And by doing so, we will have created this here. This is the problem. Once we've got this, we then are either, we know the forces and we're solving for the displacements, or we know the displacements and we're solving for the forces. And that's what we're going to be doing. So that's top level, what we're doing. Let's start now. We're going to look at the simplest structure that we can look at. Not the simplest structure, we're looking at the simplest element we can look at. We're going to look at a single isolated spring. That's my door. My wife is also in the house. I don't just ignore it when people ring at the door. Okay, so we're going to look at an isolated spring. We look at springs because they're nice and simple, because they've got a stiffness which we can just define as K. So we've got a simple spring going from node 1 to node 2. We have forces that can be applied at each end. We've got force 1 and force 2, and note that these are lowercase, so these are local forces. The force on node 1 of this element, the force on node 2 of this element. Both of these nodes can be displaced, and we'll say this is Q1 and Q2. Okay, we can be displaced in just in terms of length in this problem, okay, because it's a uniaxial spring. Sorry, it's not a uniaxial spring, it's a two-force member, okay. We aren't looking at bending in this problem, so we're only looking at extension and how we relate that in this problem, okay. So we need to describe the spring stiffness as well. Stiffness, forces, and displacements. Okay, so in order for this spring to be in equilibrium, okay, so it's not extending too far and so it's not accelerating, then the total tensile force in this spring has to be equal to F1, which has to be equal to F2, that's what I'm pointing at, which has to be equal to minus F1. So we'll say for equilibrium, F is equal to F2, which is equal to minus F1. And here, this is just the tensile force in the spring. We can also recognize that the spring under a positive tensile force is going to extend, and we generally call this extension by a delta, okay, or sometimes call it delta L. Let's call it delta L, okay. So we'll say the spring will extend under tensile load by delta L. Okay, delta L is the change in length. And hopefully you can see that that's just going to be equal to however much Q2 extends minus however much Q1 extends. Okay, so if these two are the same amounts, the spring has just been translated, which means it hasn't extended at all. So Q2 minus Q1 is equal to DL. Okay, now we can use some things we already know to describe the relationship between the applied forces, the displacements, and the spring stiffness. Now we know that Hooke's law applies. We're going to say Hooke's law applies for this spring. We'll say it's a Hookean material. And then we can use the constitutive relationship to come up with a relationship. F is equal to K dl. Force is equal to stiffness multiplied by displacement. So we say the force on the spring, and again this is just the tensile force. It's not, well, force, it's either equal to Q2 or minus Q1. It can be equal to the stiffness of the spring multiplied by the change in length. That's just Hooke's law. Okay, now we've already got an expression for dl, it's just this thing here, so let's substitute that in. Q2 minus Q1. And since we've said that F is equal to F2 and minus F1, that gives us two expressions to replace this with. So we can say that F1 is equal to minus K Q2 minus Q1, and F2 is equal to K Q2 minus Q1. Let's just get rid of the minus sign here. Let's see, it's K Q1 minus Q2. So what we've now got, we've got expressions relating the forces on the nodes and the displacements of the nodes and the spring stiffness. So we've got two equations. Let's put these into matrix form. So we've got the displacements. Let's put these Q1 and Q2. And I'm going to say F1 and F2 on the right hand side. I've then just got to put my matrix here. And hopefully we can see, well, F1 is equal to K multiplied by Q1 minus K multiplied by Q2. So that's K and minus K. And then F2 is equal to K minus K multiplied by Q1 plus K multiplied by Q2. So we end up with this expression here, and what we've just produced is we've just produced the KQ equals P description for a single spring element in local coordinates. So that is K subscript E QE vector is equal to PE vector. So we've just produced this. This is local stiffness for this element. I should put local stiffness matrix really. This is then my local displacement vector. And then here, this is my local force vector. So we've got this problem here. We've put this into matrix form, and we've got this. So let's say, for example, I have values for F1 and F2, and I want to solve for the two displacements. So in this case, we would know values for F1 and F2, and we're trying to solve for the Q's. So let's say we've got this here. Okay, so this is known. K is just a number. Okay, K is just a value in pascals, and then Q is what we want to know. So we then would change this to Q1, Q2. It's going to be equal to the inverse of K, K minus K minus K, multiplied by F1 and F2. So let's think about how we do this. Well, it's a 2 by 2 matrix. So I swap these over and I change the sign of these, and then I divide it by the, I've forgotten the word for it. What's the word for it called? The determinant. Divided by the determinant of the matrix. Wow, that was worrying. So that's going to be K, 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 divided by K squared minus K squared. So this, we've reached a problem. We reach a singularity with this. We cannot define this because we end up with a 0 on the denominator. So we've reached the problem here. Now what this means is that if we have two forces on our isolated element, we cannot solve for Q1 and Q2. Let's think about what that means. So since the matrix is singular, we cannot invert it. And this means we cannot solve Q1 and Q2 for this particular problem knowing just F1 and F2. Now, even though we can't define this, we can sort of think about what dividing by 0 sort of gives us. It's a really big number, basically. The physical significance of this is actually that since we cannot define this, the reason we can't define it is because if we have a spring like this, I've got my two forces, F1 and F2. There are infinitely many solutions because this whole spring can displace, the whole spring can move, okay? So the whole thing can accelerate according to Newton's second law because of different combinations of F1 and F2, which means there are infinitely many solutions of Q1 and Q2. So the physical significance okay, and I don't like dealing with infinities, so we'll just say there is no unique solution for the value of Q1 and Q2 for the problem as we've described it. So in order to solve for this, we need to constrain the problem, okay? We need to apply some boundary conditions for the problem. So let's say, going back to this spring, let's say we change it to a built-in at this side, okay? What we've done then is we've said there is still a displacement Q2 that can be moved. Q1 has to be equal to 0. Okay, so by building this side in, we still have F1, it's just the reaction force, but the displacement here has to be 0. So we will amend the physical problem. Okay, we'll amend the physical problem by enforcing a built-in support at the leftmost node. Okay, by doing that, we've enforced Q1 is equal to 0. Has to be equal to 0 in this problem now. So let's look at our matrix problem. We've got K, 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 Q1, Q2 is equal to F1, F2, and we've now said this one's equal to 0, okay, which means that actually we can get rid of this whole column in the matrix. We can get rid of it, and we can very easily solve now for Q2. Since Q2, if we know F1 and F, well, if we know F2, for example, it's simply going to be equal to F2 divided by K. Okay, and we can very readily observe then as well that F1 is going to be equal to minus K multiplied by Q2. In this case, so that's just writing out these equations. So this comes from writing out this equation and rearranging for Q2, and then this one is just writing out this topmost equation with the boundary condition enforced here. And we should be able to see if we substitute this value of Q2 in here, then we end up with we end up with minus k multiplied by f2 multiplied by 1 on k, which is minus f2. Okay, so we've just produced a matrix method to say here that Q2, let's write this out this way, let's say F2 is equal to K multiplied by Q2, and down here F1 is equal to minus, sorry, that should be minus F2. Now this isn't anything particularly groundbreaking we've just done, because we've just said the force on the spring is equal to the stiffness multiplied by its change in length. Okay, remembering that dl is equal to Q2 minus Q1, which for this case is equal to Q2 minus 0, which is equal to Q2 in this case. So we've done that, but we know this is correct. And what we've done here is we've just said that the reaction, F1, has to be equal and opposite to whatever we apply to it. Okay, so we went a long way through taking, let's think about what we started here. So we said we're going to start with the spring, with these equations. The equations we started at were, we said here that the applied force was equal to, for equilibrium here, the F1, which we ended up saying was the reaction when we built it in, was equal to the applied force at the end, times by minus 1. And we then introduced this here. Okay, we said this is from Hooke's law. We went all the way through, developed it as a matrix, put it into matrix form, said we can't solve it in matrix form because there's infinitely many solutions. And so that brings the idea of boundary conditions. Okay, boundary conditions are the way that we solve problems with too many solutions. We say we know something about the shape of the solution. So we did that, reduced the number of degrees of freedom of our problem, and enabled us to solve for both Q2 and F1 in this problem. Now, that might sound like we've gone through something just for the purpose of it, but we've gone through this methodology to show you how we look at producing a stiffness matrix for a single element. And that we've been able to go through that, put it into matrix form, show that we can't solve it without boundary conditions, but importantly, when we solve it, we get an answer that's physically correct. We know that's the right answer because it's based upon, it gives us the same answer to if we looked at it without the matrix method. Okay, and it will do because we've implied this up here and then we've carried it through, but we've shown that the methodology of applying boundary conditions enables us to get the right answer, and it enables us to get a system of equations that we can solve. So we're going to extend this methodology to multiple springs. So this one here is just one spring, and what I'm going to move on to next lecture, these lectures are going to be short just to keep your attention in this modern age. How old do I sound? We're gonna put another spring connected onto this, and then we're going to do it again. And we're going to look at the difference between different sorts of boundary conditions, and then we're going to move on to looking at bar elements and how we account for the fact that we haven't got springs, we've got bars, and actually very, very little changes in the analysis. We just end up saying K is equal to EA on L. Okay, so we're going to be going through that. This is going to be a lot of pen and paper, lots of pen and paper work. We're going to end up producing, like I said, some very large matrices. So we've got matrices with many, many rows in, and a big vector. Okay, so we've got a problem like this. This is a really big matrix here. Now, we're going to be formulating this, and you're going to be trying to solve for these a lot of the time, which means you've got to do something with this matrix. We can invert it. We could use that. Often computational techniques don't do a direct matrix invert to compute things. We would just put this in as a system of equations and we'd solve it. I will go through a couple of smaller exercises doing hand techniques. So we'll do Gaussian elimination, which is where we get rid of this whole side of things and reduce it to a system of equations we can solve. because I know for some reason you guys all love pen and paper as opposed to doing things on computers. And we'll do that for a few smaller matrices, but as we get to larger ones, you know, even looking at this matrix here, this would produce a 10 by 10 matrix. I do not want to solve that by Gaussian elimination. I'll make too many mistakes doing that. Okay, so we're going to be going through this. I'm going to do a couple more theory lectures on springs, and hopefully you guys are following with this. If there are questions, you know where to find me. Drop me a message on Slack, pop a comment on the YouTube video or whatever, and I hope this is enjoyable for you guys. I'll see you guys in the next lecture. Catch you all soon. Cheers.